Okay, what I want to focus on today are reactions. Because the two videos I've done for this unit 3, I didn't do too much with the reaction. I only just really go over lots of examples. And then on Wednesday, now your test is going to be on Monday, a week from today. So on Wednesday, I'm going to go over a practice test with you. And so most people feel, and you can have a 3x5 card on both sides as well. And all right, so let's talk about reactions. Okay, so this unit, acids and esters. Now, the thing about acids is they're more polar than alcohols. So when I ask you for boiling point discussion on a series of chemicals, acids are going to be first, alcohols second. Alkanes are going to be at the bottom. And then everything else is going to be in between. Okay. So let's look at acids in general. Now, acids in different pHs will be either ionized or not. And we're going to see in Unit 4, amines, nitrogen compounds, are going to be the opposite of acids. So I will definitely ask this on the test Monday. Okay, say we have a pH of 9. Very alkaline or very, very basic. So let's look at that is 1, 2, 3, 4. Butanoic acid. And we put butanoic acid in an alkaline environment. What's going to happen, like sodium hydroxide or potassium hydroxide, this guy and that hydrogen are going to form water and leave us with the acid salt. So this is going to be so that's going to be sodium butanoate. So this is the part, and that together make it an acid salt. Well, that's a pH of 9. What about a pH of 2? So this is a pH of 2 is going to be an acidic solution. And in that case, there's nothing that can pull that H off. So no reaction. So make sure you understand that, because it's going to come back to us in Unit 4, but it's going to be the opposite. And on the test on Monday, it's going to be same as test 2, naming reactions, intermolecular forces. Every single test does that. And also I'll be doing the corrections as well, like the past tests, C or D. You can correct your answers for half credit. Now, on that, I want to stop for a second. Now, when you turn in a corrected test, you will see nothing or a 1. If you see a 1 there, that means I corrected your test. Okay? Now, to turn in your corrected test, make sure you scan your old test with the corrections. Okay? All right, so does that make sense? All right, so now when you have an acid in there and another acid, they form something called a dimer. A dimer is when the two acids hook up, and they hook up like this. That's another reason they're particularly polar. It's because of the dimer formation. All right, so there's neutralization with acids. They can be neutralized by the opposite of an acid, which is a base or an alkaline substance. Now, in the presence of alcohols, that's where we get into some interesting combinations. That's where the formation of an ester comes from. So an ester is an acid plus an alcohol. So last unit, we had an aldehyde slash ketone plus an alcohol. Happens again with an acid plus an alcohol. Alcohols like to react. Okay, so that these two together forms an ester. Now there's 3 ways to make an ester. With an acid plus an alcohol, or the acid chloride, or the anhydride. As far as yields go, the least yield is going to be an acid plus an alcohol. The most yield is the acid chloride plus alcohol. One in the middle is the anhydride, and that's when we used to make aspirin, the anhydride. Okay, so let's look at an ester. Okay, so we've got 1, 2, 3, 4. So it's 4 carbon acid. Three carbon alcohol. So you've got a secondary and primary backbone. So the primary is going to be the acid side. Secondary is going to be the alcohol side. So we need a 4 carbon acid base and a 3 carbon alcohol to get this ester. And we're going to make it 3 different ways. So we need to start with a butanoic acid. Plus propanol, 3-carbon alcohol. Now to name this ester, first you name the alcohol part. So it's going to be propyl. So it's just like naming a salt, butanoate. Okay, so that's one way to make that ester. All right, let's do it with the acid chloride. Now, in acid chlorides, the way we're going to do it is the common way. So we need butyl chloride. Excuse me. Butyl chloride plus the alcohol. Okay, that'll give us the best yield. Now, the reason why we're getting the best yield is because the acid chloride is so unstable. By the way, I have yet to finish grading your test. That's almost done. I made good progress in lab last week. I'll have them done tonight though, 100%. Okay, then the last, okay, let me back up again. So the acid chloride, the butyl chloride is very, very unstable. It'll give you the most yield because it wants to become more stable, but its shelf life is really short. So they're very expensive because they don't last long on the store shelf or in your lab. They just react with air and everything else. Or they want to, in air, they suck the water out of the air and form the acid version of it. The anhydride is a nice compromise. So the anhydride, think of it as 2 esters together. Okay, so we're going to have so this is going to be the anhydride is spelled 2 ways, 1 N or 2 N's. So what's going to happen is it's going to kick off one of the acid parts of the anhydride. So that's the 3 ways to make that ester. Okay, that's going to be another question on Monday's tests. I'm going to say, make this 3 different ways and tell me the yields. So basically, whenever you make an ester, you have to figure out the two backbones, the primary, secondary backbone, and then come up with an acid for the primary and an alcohol for the secondary every single time. Now, biochemically, you've got fats, oils, and waxes. All of them are esters. So that means they have an alcohol backbone, an acid backbone. The fats and oils, the alcohol is a triple alcohol. It's called glycerol. And then there's an acid component. Waxes are simpler. It has one of the very long alcohols, very long acids. And there's only one on the alcohol, there's only one OH group, not three like glycerol. So I may ask you a question like draw a simple wax. So all you're going to do that is, you have something like, 18, 20 carbon acid. Made it to a long, long alcohol. So let's use stearic acid, which is C18. So we're going to go and let's make that to let's make that to a 24 carbon alcohol. And that would be like beeswax or something like that. Paraffin, very simple wax. Now, a fat or an oil is basically the same thing, except the alcohol has 3 hydroxyl groups on it. So it looks like this. And this can be these 3 acids can be any variation. It can be a mixture or it can be all the same. Mostly it's a mixture. The only way you'd get a pure, like trioleate, for example, is a triglyceride with 3 oleic acids. Usually they're a mix though. And if it's an unsaturated acid, it can be cis or trans. The natural ones are cis, the adulterated ones are trans. Trans are bad. One of the main reasons trans fatty acids are bad, actually there are 2 reasons. One, lipase is the enzyme that helps your digestion. It breaks apart the triglyceride into its acid form and its alcohol form. That's lipase. Lipase works with cis. So if you throw trans fats in there, its efficiency is much lower. So basically, lipase is in your small intestine. So your stomach dumps into the small intestine, And that's where the lipase is located, and that's where it starts breaking down the fat. Now, there's a problem breaking down fat. This is a water environment we're talking about. Fats are very non-polar. So what happens is your liver produces bile, B-I-L-E, and bile is like soap. It breaks up the fat into little bitty globules. So the lipase enzyme can work more effectively. So if you ever gallbladder removed, like for example, my daughter had her gallbladder removed, and you can't store the bile. Your gallbladder is where the bile is stored that the liver makes. You still make bile, and just there's no place to store it. So your capacity to digest fats is diminished quite a bit. So you have to be careful what you're eating. But that's one problem. The second problem is biological membranes are designed with cis fatty acids, not trans fatty acids. So that your membrane will be compromised, its stability. Now, I was raised on trans fats because in the 50s, my mother thought it was healthier to use Crisco vegetable oil as the grease for making baking pies and cakes and all that stuff. And Crisco in those days produced a ton of trans fats. So you're looking at the result of trans fermentation. So my mother never stopped using Crisco. Crisco almost went out of business because all their fat is trans, not cis. So what they ended up doing is blending oil rather than hydrogenating the oil, the consistency they want. So Crisco's doing fine now, but back in those days, it was bad. So anyway, cis is the way to go. So if you have an adulterated fat, meaning that there's trans double bonds in there, that is an unhealthy fat. You've heard the expression healthy fats, right? Like olive oil, avocado oil. And the reason why they're claiming it's more healthy, seed oil is usually polyunsaturated, multiple double bonds. Multiple double bond oxidize more easily than single double bonds. Double bond is the point of oxidation. The problem with oxidating seed oil is you end up polymerizing. Polymerized oils are bad. The other problem is you create aldehydes once you oxidize that double bond. Aldehydes are fairly unstable in the body, and they form all kinds of stuff. For example, there's in between the double bond on polyunsaturated, there's one carbon between them. So when that oxidizes, you form a 3-carbon double aldehyde called malonaldehyde. That's what my first graduate research was on, malonaldehyde. And I developed a way to test for it. But the way I developed to test for it is how they interact with DNA. So the malonaldehyde actually changes your DNA. Cancer. Now it's easily, if you cook very much and you have your jug of fatty oils to cook with, like corn oil or canola oil, something like that. After the oil gets used, the bottle gets sticky. Have you noticed that? That's polymerized oil. And that stuff is really bad for you. That's why they say seed oils are not good for you. That's where the healthy, unhealthy part comes into play. So anyway, my principal investigator, PI, lost his money, his funding, so I ended up having to get another principal investigator. Hence, lipids. Anyway, so healthy fats, one double bond, like oleic acid. Omega-3 fatty acids, another healthy fat. Now, oleic acid has one double bond, but it's an omega-9, not omega-3. You have to get linolenic acid, 3 double bonds, omega-3. You get that from fish, cruising fish only, not flat fish like halibut. They sit on the bottom and wait for their food to float by when they grab it. Cruising fish are always swimming. And that swimming muscle is what develops the omega-3s. The darker the meat, the better. On salmon, for example, there's that long strip that's dark. Everyone either cuts that out or just doesn't eat it. That's where all the omega-3s are stored, in that long, dark strip. And keep that in mind when you scrape it away and cut it out. Okay, so now this is the simple fat. Meaning it has no phosphorus compounds in it. Membranes are called phospholipids because one of the esters is a phosphoester. It looks something like this. Doesn't matter what these two are. The third one, though, has a phosphorus ester. The phosphorus ester comes from phosphoric acid. Phosphoric acid acts just like any other acid, plus an alcohol will give you a ester. Now, the thing with phosphoric acid, it's got 3 OH groups on it. That means it can form a triester, one for each OH group. What happens is it forms 2 of the 3 will form into an ester. Now, this thing here is called choline, a very important biological molecule. Choline is a combination of an alcohol plus an amine group. So by itself, it looks like this. Choline. Biochemically, it's very ubiquitous. There's a lot of it floating around. Okay, and this is called it's lecithin, and I'm not spelling it right. A block. Lecithin structure. Lecithin. I don't know why I blanked out on spelling it. Now, lecithin is an emulsifier, meaning it acts like soap. Has anyone in here made mayonnaise from scratch? How do you make your mayonnaise?
And it's oil, egg, salt, pepper. Repeat.
The important part is the egg part. It's an egg yolk. That's where the lecithin is located. Whenever you make anything, it's like a Caesar salad. Has an egg yolk in it. Make the emulsion. Mayonnaise is an oil and water emulsion. So I was at a friend of mine's wedding and her, actually, I was at a friend of mine's daughter's wedding. And my friend's boyfriend, thought he could cook really well. He was an ER doctor. And, we made satay, which is made with peanut butter and it's an emulsion. So here we have 80 people waiting to get their satay and the emulsion broke. Because he used too much heat. And he didn't know what to do. I just said, just add a couple more egg yolk. Solved the day. It was so easy. And here he is, a fancy doctor. Anyway. Okay, so lecithin is a very common emulsifier in the body. It's also used in making cellular membranes. Membranes are really important because it divides water-based reactions and puts a non-polar barrier between the water-based reactions. Our body is a sack of water divided up into little bitty compartments by membranes. And this is what the backbone of the membrane looks like. It's from here. All right. Now, don't forget, review your Unit 2 stuff as well. There'll be a little bit of Unit 2 in there. On the reactions, like if we have, like butanol plus propanol gives us a hemiacetal, for example. So we have so don't forget to study Unit 2 stuff, mainly reactions. Okay, so acid reactions are neutralization, dissociation, say neutralization, dissociation. Ionic states in different pHs. Okay, so neutralization would be acid plus base. Okay, for example, acetic acid plus sodium hydroxide. So it's going to form the acid salt and water. Now in 305, you did not do any acid-base titration. That was the part of the lab that I cut out because we missed a week. Basically, aspirin is an acid. So you can neutralize aspirin with a base. And you can determine the number of moles of base it took to neutralize the aspirin. And you can figure out how much is there, also how pure it is using that technique. And that's called acid equivalence. Okay, already talked about the different ionic states in different pHs. Dissociation, we take acetic acid again. The IUPAC name for acetic acid is ethanoic acid. I'm going to spell it right. Acid, or acetic acid is common name. Vinegar. Okay. So dissociation means that this H comes off. And the H that's attached to the O comes off, not the other H's. Other H's are very covalently bound and are very stable. The one that's not stable is the one attached to the O. So what you end up doing is and this is a hydronium. Hydronium ion. Most of the time, they don't write H3. Oh, they just write H plus. So basically, this guy and that guy form that. So strong acids dissociate 100%. Weak acids are less than 100%. All organic acids are weak acids. The only strong acid we have in our body is in our stomach. That's hydrochloric acid. Other than that, everything is weak. Okay, intermolecular forces. We have acids. Alcohols, alkanes. And then everything else is going to be here. So we have aldehydes, ketones, ethers, alkenes. So strength, boiling point, melting point, and surface tension. So acids have the most, alkanes have the least. Okay, also, we've got the nomenclature. So biochemists use the delta. Chemists use the IUPAC. Nutritionalists use the common. So let's so if we look at oleic acid, the IUPAC name is going to be the way I have it drawn here, the trans double bond. It's going to be 9-octadecanoic acid. The other way you'll see it written is octadeca-9-enoic acid. Okay, biochemist is going to use this delta. Delta starts with the acid group as bicarbon number 1. This is the number of carbons and how many double bonds. The delta means where is the double bond located? Carbon number 9. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is going to be 9 here. A nutritionalist is going to look at how far in on the omega end. So this is the omega end. This is the acid end. Okay, omega 9 means we go 1, 2, 3, 4, 5, 6, 7, 8, 9. The problem with the omega naming is it doesn't say how many. It just says where's the first one counting from the end. Where the delta is much more precise. It says how many carbons are there, how many double bonds are there, and where the double bonds located. And then the IUPAC name, the octadecanoic, also says where the double bonds are. Okay, so if, for example, now these are all cis, the way these are drawn. Let's look at oleic acid. Where's that? Over here. That's drawn as a cis configuration. That's drawn as a trans configuration. Now, whenever we hydrogenate a double bond, trans is more stable than cis. So whenever you hydrogenate like a fatty acid with 3 double bonds, frequently not all 3 double bonds get hydrogenated. 1 or 2, and the other one will revert to trans from cis, because trans is more stable than cis. So whenever you partially hydrogenate, you get a mixture of cis and trans, even though you start with all cis, which is the problem Cisco had with their substitute for lard. Okay, so this is the reaction to create lecithin. As we start with the phosphoric acid version of the fatty acid on the glycerol backbone. Then we throw in an alcohol, choline, and then this guy, that's where the ester is formed. Now, choline is also a neurotransmitter. Neurotransmitters work by making the nerve gap or the synapse gap work. And there's different neurotransmitters. Choline is the most common one. Pesticides used to work by, what happens is and this is a synapse for a nerve. Okay, as the neurotransmitter goes across here, it'll land on a receptor, and then the nerve fires. The problem is you have to remove the neurotransmitter so that it can fire again. Otherwise, it'll get tied up and be dead, basically. So, and this is done by the enzyme cholinesterase. So the enzyme cholinesterase, if it's inhibited, the neuron stops working. So early pesticides during the 50s and 60s were cholinesterase inhibitors. That's the way they work. So the insects, their nerves shut down, and then they die. The cholinesterase inhibitors are very dangerous because they can leach into your skin, right into your body. When I had my farm, we used to spray organophosphate pesticide. And you start with a concentrated bucket of this stuff, 5-gallon bucket of it. You put it into a 500-gallon sprayer, and then you fill it up with water, let it mix, and then you go spray it. I had walnut orchard, and spray the trees. So, on the farm, you're always under a time crunch, always. We never relax. It's an awful job. And so I was on a ladder, sprayer 5 gallons of concentrated organophosphate pesticide. By the way, there's no top on it, open 5 pound top. Fortunately for me, I had a rubber suit on, including a respirator. Had I not had that on, I wouldn't be around. I would have been dead in about 20 seconds. And I ended up slopping it onto my leg. A lot of it. And of course, everyone freaked out. They're changing me out on water and all stuff. But had I not had that rupture on, it would have been absorbed into my skin and better than normal. So organophosphates are usually not used anymore because they're so toxic they kill everything. They work really well. Pesticides are, my first wife worked in the environmental toxicology department at Davis. She was a bench chemist. And she used to work with this nasty stuff. Another chemical called toxaphene. And that they chlorinate randomly this alkane. So you end up with all these different versions of the chlorinated hydrochloride. So the insects kind of get tolerant, build up tolerance for it. But it's really bad stuff. They've outlawed it. It's, of course, she was working on it. So that department was very interesting department studies. Yeah, stuff that would run through that department. Okay, sorry. All right. Now I do have a unit 3 dry land. So, whole bunch of reactions. And I also have the answers. Here's good old choline. So Wednesday, I'm going to review reactions again. And your typical reactions. So that's what I had for you today. Kind of a broad review. On Wednesday, I want to go over a practice test with you. And then maybe test on Monday. The length of the test is going to be similar to the test 2. One length quality. So you should be, you'll have 2 hours to do it, but you probably won't be using 2 hours. So any last minute questions? Let's start lab. What time is it? It's 10 to noon. So let's start lab at 12:15. And again, it'll be a fairly short lab. And if you don't, it's okay if you don't all come at once, because the bottleneck is going to be the infrared spectrophotometry. So I'm working in particularly Monday groups. Monday groups work 2 to a group. Wednesday group 4 to a group.